In this video, we're going to talk about section 3.5, which is about implicit differentiation. Let's look at the introduction first. An equation of the form y equals f of x is said to define y explicitly as a function of x. On the other hand, there are some equations that are defined implicitly by a relation between x and y. So an example of an implicit form would be x squared plus y squared equals 25. And then an explicit form would be positive or negative. The square root of 25 minus x squared is equal to y. So let's suppose we have an equation that defines y implicitly. So in other words, it's not solved for y. And we want to find the derivative of dy dx. One approach might be to solve the equation for y explicitly and then differentiate using the formulas that we have studied. However, for some functions that are defined implicitly, it is very difficult, and in some cases it may be impossible, to solve for y. Fortunately, there is a method for differentiating these types of implicit functions. Of course there is! My God, math is so beautiful! And this method is called implicit differentiation. Yay. So let's look at the procedure for implicit differentiation. First of all, what I want you to do is not solve it for y. Again, because it can either be impossible or difficult. What we're going to do is we're going to differentiate both sides of the equation with respect to x. And remember that y is a function of x and that we use the chain rule with differentiating terms containing y. So in other words, if I'm taking the derivative with respect to x of y squared, I would do this as 2y times y prime. Don't forget those y primes, it's super important. You also could write that as 2y dy dx, either way. So the second step is once you've done that differentiating of both sides, you're then going to collect all the terms that have your dy dx or your y prime, whatever your preference is. You collect them on one side of the equation and you collect other terms on the other side of the equation. And then you're going to factor out your dy dx or your y prime. This is a fun part. Next, you're then just going to solve the resulting equation for your dy dx's or your y primes, whichever ones you're using. So let's look at an example. So for this one here, if I were to take the equation of a circle with radius 5 and solve it explicitly, the first thing that I would get is plus or minus the square root of 25 minus x squared. And if I want to take the derivative with respect to x of y, I would just have this plus or minus in the front. Also, I would rewrite this first as 25 minus x squared to the power of 1/2. And then using the chain rule, I would take the 1/2 and I would bring it down, 1/2. And then I would take the 25 minus x squared, leave that alone. And I would reduce the power by 1, so I would end up with negative 1/2. And then I would take the derivative of the inside. And the derivative of 25 is 0. And the derivative of negative x squared is going to be, bringing that 2 down, a negative 2x. And so y prime in this case is going to be plus or minus. Now, this negative right here, that's not going to affect the plus or minus. Okay, so that negative doesn't make it negative, because think about that. If I take a negative times a positive, that's going to give me negative. If I could take a negative times a negative, that's going to give me a positive. So this pesky little negative right here is going to keep this as plus or minus. It's not going to change it at all. All right. Next, I'm going to multiply the 2 and the 1/2, and those poof cancel. And then this 25 minus x squared to the negative 1/2, that is in the denominator. And I'm going to rewrite it as a square root. And then this x is the only thing I got left, and that has a positive power. So that's going to be my equation for my derivative. Next, let's do it using implicit differentiation. So what I'm going to do is I'm going to take this side, and I'm going to take the derivative of it. I'm going to set it equal to the derivative of the other side. So I'm going to take d dx of x squared plus y squared, and I'm going to set that equal to the derivative of 25. When I'm taking this derivative here, I'm going to bring the 2 down. So I've got 2x. And then the derivative, remember, the derivative of x with respect to x is just 1, so I don't have to write that 1 down. Next I've got plus. Next I've got y squared. I'm going to take that derivative. So I'm going to have 2y, and don't forget the y prime. Or you can write it as dy dx. It's not 1 though, that's important. And then I'm at my equal sign. And then what's the derivative of 25? Yeah, don't forget that. That's just a number. That actually makes it easier to solve. So now what I'm going to do so I already took the derivative of both sides. Now what I'm going to do is anybody with a y prime is going to be on the left. So I'm just going to determine that the left side is the y prime side. So 2y, y prime gets to stay on the left. And this 2x, I'm going to subtract and move it over to the right. Now what I need to do is solve for y prime. So notice, for y prime, it's being multiplied by 2 and y. So how about I divide both sides by 2 and y? All right, let's do that. Negative 2 divided by 2, negative. X divided by y, x over y. And that's my derivative. It's okay that it has y in it. If we knew what y was, we would substitute that back in. Also, let me point a couple of things out about signs that I haven't done in the last few lectures, and it's just kind of driving me kooky. Okay. When you have signs in fractions, why did I write it like that? When you have signs in fractions, the only thing you really don't want to do is put it with the denominator, unless the denominator is big and you can distribute it out. You never really put it with the denominator. You can take the sign and put it in front of the fraction, or you can take the sign and you can put it in with the numerator. Okay, so just a little side note. You're welcome. Now let's look at this next problem. If you can take this derivative implicitly, what are you going to do first? What's the first step? Exactly. Take the derivative of both sides. So I'm going to take the derivative of this side, and then I'm going to take the derivative of this side. So I'm just going to squeeze that writing in there because I'm going to need to save room for myself. All right. Let's take the derivative of this side. What happens to the power? Good. Comes down. 5y, reduce the power by 4, and then y prime, because I didn't take the derivative of something with an x in it. Ooh. This one's product rule. I have a chunk of algebra times another chunk of algebra, so I need to use the product rule. So remember how the product rule works. I'm going to take the first and I'm going to multiply it by the derivative of the second. And then I'm going to take the derivative of the first and multiply it by the second. Let me show that one more time and let me color code it for you guys. All right, here's my first. And I do first times the derivative of the second plus the derivative of the first times the second. Okay, so that's how that goes. Well, I didn't really color coded it, but I dot coded it for you. All right, carrying on. Again, product rule. Right over there. Product rule. Next, I'm going to take the derivative of 5x to the 4. So I'm going to bring the 4 down. 5 times 4 is 20. And I got 20x cubed. Next, and don't forget this part, because sometimes after doing that whole left side, students forget this when they get to that. But what's the derivative of 12? Yeah. Don't forget to smile at yourself at some point in the problem. You have a 0. A lot of times when you do these, don't forget that. Okay. Let's go ahead and note which ones have y primes in them. All right, this one has a y prime. This one has a y prime. This one does not. This one does not. All right, so we're the ones without a y prime, we're going to move to the right side. The ones with a y prime, we're going to keep on the left side. So I've got 5y to the 4 times y prime. For this one, I'm going to multiply things together. Please don't leave it unmultiplied. It's super uncool. We don't want to be uncool in calculus class. Ick. All right, now I'm going to write minus 6xy squared, and minus 20x cubed. Oh! Apparently, my dog hears something. Oh, good Lord. All right, I'm back. I love my dog, but I wish that her hearing was worse. Holy crap, she barks at everybody. Okay, anyways. All right, now that I've moved everything over from the left side and the right side, I'm going to do some factoring. So remember, I got a y prime here, and I got a y prime here. So I'm going to factor y prime out of the left side of the function. And everything else just goes along for the ride. For this left side, once I factor the y prime out, I just have 5y to the 4. And once I factor the y prime out here, I'm going to have 6x squared y over here. So now I need to solve this for y prime. Keep in mind, if I had like 3y prime equals, I'm just going to write a scribble. If I were to solve for y prime, what would I have to do? Yeah, I would have to divide that side by 3. So that's what I'm going to do here. I'm going to divide both sides by this thing. And then I end up with y prime is equal to negative 6xy squared minus 20x cubed, all divided by 5y to the 4 plus 6x squared times y. There aren't any numbers or variables that I can cancel out of anything, so I'm just going to leave it like that. If I wanted to factor the negative out of it, I could, but you're not required to. All right, well, let's find equations of tangent lines with implicit functions. So I need to find the equation of the tangent line to the curve x to the 2/3 plus y to the 2/3 equals 4 at the point of -3 square roots of 3, comma 1. So first, let's find the slope of the tangent at x equals -3 square roots of 3. That basically means I need to find y prime. I need to find y prime. And then because it's implicit, what I'm going to do is I'm going to plug in the point because I'm going to have y's and I'm going to have x's into it. And that's going to give me the slope of the tangent. So let's do that. And after that, then I'm going to find the equation. And I'm going to use that y minus y1 equals m times x minus x1. All right, so we're going to take the derivative of both sides. I'm going to take the derivative of the left side and the derivative of the right side. So the derivative of the left side, I'm going to bring the 2/3 down, and I'm going to end up with 2/3 x. Now 2/3 minus 1 is going to be minus 1/3. And then that's an x, so I don't need an x prime. Next, I've got my y. I'm going to bring the 2/3 down. I've got 2/3 y to the -1/3, and then that's times y prime. And then don't forget the left side. What's the derivative of 4? That's right, don't forget your smiley face. Right, anything without a y prime is going to go on the right side. Anything with a y prime is going to stay on the left side. So I'm going to move that other term over. So I'm going to have 2/3 y to the -1/3 times y prime equals -2/3 x to the -1/3. Now that I have everything over to the correct side, I'm going to solve for y prime. So I'm going to divide both sides by 2/3 and y to the -1/3. And then I'm going to simplify. And actually, I'm going to bring it over here. Okay, for my 2/3 and -2/3, that's going to cancel with the negative behind. And then notice both my x and my y have negative exponents. So I'm going to rewrite it. Gosh darn it. My 2's often turn into 3's. I don't know if you've noticed that particular aspect of my dyslexia while watching my videos. All right. But anyways, yeah, cool. We're going to go ahead and we're going to plug in the stuff that we need to plug in. So y prime is equal to this. So let's plug in the point. This is my x coordinate. This is my y coordinate. So y prime is going to equal, now y to the 1/3 is 1 to the 1/3 power. And then x to the 1/3 is like saying -3 square roots of 3 to the 1/3 power. So really, do I want to simplify that? I mean, the 1/2 power to the 1/3 power is 1/6. And then I've got the cube root of 3. You know what? No, that just seems excessive. Who knows? Let's just leave it like that for now. We're good. That's my slope value. The other thing, actually, though, that I can do, okay, sorry, I lied a little bit. Whenever I take the 1/3 power of something, the sign just gets to come outside. So I'm just going to write it like that. All right, so let's go ahead and plug this in. So I have y minus y1 equals my slope value, which is really horrendous, times my x minus my x value. Ugh, I can't leave it like that. Ugh, I want to, but I won't. All right. I'll distribute this out. And I've got negative x all over this 3 square roots of 3 to the 1/3. And then this will be minus 3 square roots of 3 all over 3 square roots of 3 to the 1/3. Now for that second piece, for this second piece right here, I can really simplify that by subtracting their exponents. So I would have 3 square roots of 3 is to the first power, and then subtract that by the 3 square roots of 3 to the 1/3 power, and I'm going to end up with, so this y over here, by the way, I'm just going to add 1 to both sides just to get that over with in that space. And then I'm going to have this little bar, this little, I can't even say it, this little bad boy. I'm not a fan of this problem. Which is not true. I'm a fan of problems, but maybe, I guess not this one. 3 square roots of 3 to the 3/3 minus 1/3, 2/3 plus 1. I could simplify this a little bit, because if I square, if this is to the 2/3, if I square 3, I'm going to get 3. If I square 9, I'm going to get 9. So this would really turn this into the cube root of 27, which I can do. So negative 27 plus 1, that'll give me 26. Ick. Well, I guess I'm glad I did it. This would be one of those things that, like, my grandparents or my parents would have said, like, put terror on your chest. And I think to myself, I'm not sure I'm that type of lady. For this next one, we want you to find the second derivative by implicit differentiation. Now, don't worry, this will work out fine, but it does take a lot of time, and I'm probably going to use up 2 slides. So make sure you've got a fresh piece of paper. First, I'm going to take the derivative with respect to x of both sides. So here, the 4 is going to come down in front. So I have 4x cubed. And then 4 is going to come down here, plus 4y cubed y prime. So I'm taking the derivative with respect to x. So when I take the derivative of the y, I get the y prime. Don't forget the right side, the derivative of 16 is 0. So get your smiley face on. Next thing I'm going to do is this one's going to go over to the right, and this guy's going to stay here on the left. So I'm going to have 4y cubed y prime equals 4x cubed. And then I'm going to divide both sides by 4y so I can solve for y prime. And then my 4's cancel. And I forgot a minus sign when I moved my 4y x cubed over. And so this is going to be negative Look at that, my spidey sense was going off. I had a mistake. I found it before I edited it. How exciting. Oh, math, constantly keeping us humble. Okie dokie. Well, that's my first derivative. Now I need to take the second derivative. This is where it gets a little interesting. So we have to use a rule. So if I'm going to do y double prime, what rule do I have to use? Yeah, I got to use quotient rule because these things are dividing each other. So I'm going to do my low times the derivative of the high minus, because quotient rule is minus, and then my high times the derivative of the low. And don't forget that y prime in there. And then all over the low squared. Let's go ahead and simplify some things. I'm going to write this as negative 3x squared y cubed. This negative is going to turn into positive. 3 is going to come in the front. And I'm going to have x cubed times y squared. And here's something that's kind of magical that's going to happen. Is that, see this y prime right here? I know that y prime is equal to negative x cubed y cubed. So I'm going to plug that in here. Negative x cubed y cubed. And then I'm going to finish in the wrong color, dang nabbit. I'm going to finish the denominator. Y to the power of 3 squared gives me 6. All right, let's simplify. So negative 3x squared y cubed. I've got a negative 3 again. This is going to be x to the 6th. And then the y and y cubed is going to cancel, so I'm just going to be left with y here. And this looks suspiciously like a 2, but that's a y cubed. And then that's going to be over y to the 6. All right, let's make some changes here. Let's see what we can do. I am going to multiply the top and the bottom by y so I can get rid of that LCD. And I'm going to have negative 3x squared y to the 4 minus 3x to the 6 all over y to the 7. And then, oh my gosh, look at what's going to happen. Okay, so you may not see it, but see these guys? I've got these negative 3's right here. I'm going to factor that negative 3 out. And then next, I've got an x squared and an x to the 6th. So I can factor an x squared out. And what I'm going to have left when I do that is, from the first term, y to the 4 plus x to the 4. And then that y to the 7 in the denominator just stays as is. Well, I don't know if you remember our original function. It's been a little while since we've looked at it. But our original function, which I wrote all over the place over here, is x to the 4 plus y to the 4 is equal to 16. So this y to the 4 plus x to the 4 is actually equal to 16. So I'm going to have negative 3x squared times 16 all over y to the 7. And that I'm going to simplify, and I end up with y double prime. Sorry, this is double prime. Sorry, this is double prime. Good Lord, the dyslexia is bad with this one. We are going to have negative 3. We are going to have negative, oh my God. We are going to simplify that, and we get negative 48 x squared all over y to the 7. And holy cow, that's a fun problem. All right, I hope you enjoyed implicit differentiation. Let's review some inverse trigonometric functions. Yeah, you ready? Me too. Okay. Trigonometric functions, let's rework the original for a second. This is the adjacent side, or the x side. This is that angle theta, which is the reference angle between the x-axis and the length right here, the hypotenuse. And then this side right here, this is the opposite side, or the y value. And then we have the hypotenuse, or the r. And if you remember your rules for sine, cosine, and tangent, there's that whole SOHCAHTOA. Or back in my day, it was like Oscar had a heap of apples. So silly, all these math people and their piles of fruit. But basically, if I find the sine function, I take the ratio of the sides. I do opposite over hypotenuse, or y over r. The cosine function is the adjacent side, which is going to give me x over r. Tangent uses the opposite and the adjacent. No hypotenuse here. And so that's going to give me my opposite over adjacent. And then these other three functions, these are called the reciprocal functions because the cosecant is the reciprocal of sine. So this is going to use the hypotenuse over the opposite, or it's going to be r over x. The secant is the reciprocal of the cosine, so this is going to be the hypotenuse over the adjacent, or the hypotenuse over the x. And the cotangent is the reciprocal of the tangent, so this is going to give me adjacent over opposite, which is going to give me x over y. Now note this, the way that the regular trig function works is what you put in to the trig function is the angle, right? You put in the angle. What comes out is a ratio of sides, okay? What comes out is a ratio of sides. So that's for regular functions, but if I'm going to do the inverse trig functions, it's the opposite. All right, let's take a look at that. The opposite of it is this, where I don't feed it. What doesn't go in is the angle. What go in is the ratio of sides. What comes out is the angle. So these inverse functions, this basically is like saying the sine of y equals x. And here's the domain. And here's the range, because inverse functions, I don't know if you remember, can only be created by one-to-one functions. So we restrict the domain of the original sine function, which is the range of the inverse function, in order to get it to be one-to-one. So that's the definition there. All right, voila. These are all the rules. Understand that these are the domain and range for the inverse functions. Okay, these are the domain and range for the inverse functions. Notice what values are included and what values are not included. And understand this concept of the absolute value of x is greater than or equal to 1. This means that x can be any number up to -1 and any number after +1. Yeah, and nothing in between. All right, this little mini section of 1.5 is just reintroducing you to the inverse trig functions because we have to do the derivatives of the inverse trig functions. So if I'm trying to find the tangent of the arcsine of 1/3, let me just color code that for a moment. I've got the tangent of the arcsine, and the arcsine is also like saying the inverse sine, so just to save some space, I'm going to write it like that, of 1/3. All right, remember, what we're plugging in here is the ratio of sides. So this means that if I were to take the regular sine of theta, that would give me 1/3, which means the opposite over the hypotenuse is 1/3, which means I can write or draw a triangle for this function that's being discussed with the trigonometry. So opposite of theta is 1. The hypotenuse of theta is 3. And then I can use the Pythagorean theorem to find the adjacent, right? So here's my opposite, here's my hypotenuse, and here's my adjacent. 3 squared is 9, minus 1 squared is 8. Take the square root of that, I get the square root of 8. Don't give me decimals. Alrighty, well now, remember what comes out of the inverse sine is theta. So tangent of that theta is what I'm looking for. So I drew the rectangle, I can find it. Now tangent, remember, is opposite over adjacent. So I'm going to do opposite over adjacent. And that's going to be my answer there. Let me clarify because I feel like I didn't very well. But remember, the 1/3 is the ratio of sides. When I do the inverse side of the ratio of sides, what comes out is the angle. So when I do the reference triangle, I can then do the tangent of that angle. And that gives me 1 over the square root of 8. I can rationalize that denominator if you want to. It's up to you. But I feel like that was something we kind of did in the 90s. We don't really do that anymore. Okay, let's do the next one. This one's going to require us to use some trig properties. So get out that trig sheet. Making my reference triangle. Teaching in my living room's kind of weird. All right. I've got my stuff color coded. So remember, I'm not color coding it very well. remember that theta is equal to that inverse sine of the ratio of sides, because we put in a ratio of sides. It's not written very clearly. And what we get out is a triangle. Once again, the sine, this means that the sine of that theta is equal to 3/5. So that means if I were to draw a reference triangle, my opposite side would be 3, and my hypotenuse side would be 5. And I can say 25 minus 9, which is 16, take the square root of that, and so I find my adjacent side is equal to 4. Now, if I need to find the sine of the 2 of this, let me keep this straight. This is going to be the sine of 2 times that theta, right? And I need to use a formula for that. So that's what I'm going to do. Sine of 2 theta is equal to 2 times the cosine of theta times the sine of theta. And if you don't believe me, just look it up. So that's what I'm going to use. So the 2 goes along for the ride. And the cosine of theta is the adjacent over the hypotenuse. And the sine of this theta is the opposite over the hypotenuse. So I need to combine those together. So 2 times 4 is 8, times 3 is 24. And then 5 times 5 is 25. Cool. Can't simplify that anymore. Good job, team. So I want you to try these examples for a second. Remember what you do, okay? Let me just give you a hint. Okay, build your triangle. Build your triangle. Build your triangle based off of the thing that you have on the inside. Then, and so the build the triangle, that comes from your inside inverse function, right? And then you're going to do the outside trig. Okay, go ahead and work on it. Pause it for a second. See if you and I can come up with the same answer. Hey, welcome back. All right, I color-coded it for you. So keep in mind, my theta is going to equal the inverse tangent of that x over 1. And I cheated a little bit. I wrote it as x over 1 because I know it's a ratio. So x written as a fraction is x over 1. Be mad about it. Well, that basically means that the tangent of theta is equal to x over 1. So this is what I used to build my triangle. If you got stuck at that first part, that's okay. Go ahead and pause now and see if you can do the rest. All right, so the tangent is the opposite over the adjacent. So it's x and 1 for my opposite adjacent sides. And my hypotenuse side is going to be 1 plus x squared, the square root of, or x squared plus 1, up to you. Now, once I have that triangle built, I can go ahead and do the cosine of that thing. So now I need to find the cosine of that angle. Now cosine is adjacent over hypotenuse. So this thing is going to be 1 over 1 plus x squared, the square root of. Cool, eh? All right, if you didn't already, go ahead and try that second one. See if you can build it up. Remember, one of the tricks is treat that x as a ratio of x over 1. All right, welcome back. I took the luxury of color coding it. So let's go ahead and do this. So at this point, we know that the sine of theta would give us x over 1, and the sine is opposite over hypotenuse. So when I build my triangle, my opposite side is going to be x, and my hypotenuse side is going to be 1. And if I need to find the adjacent side, I need to do the Pythagorean theorem. I'm going to take 1 squared minus x squared, which gives me 1 minus x squared, and then take the square root of it. Now that I have that figured out, I can go ahead and take the tangent of that bad boy. So the tangent of that theta is going to be opposite over adjacent, and I just found that stuff. So this is going to be x over the square root of 1 minus x squared. All right, good job. I hope you got the same thing I did. Neato, huh? So this takes us into section 3.5, where we start looking at the derivatives of these functions. Keep in mind that if I have y equals the inverse sine of u, that means that u equals the sine of y, which gives me enough information to do what I was doing previously to build my triangle. My opposite side is u, and my hypotenuse side is 1. So that means my adjacent side is the square root of 1 minus u squared. So let's take the derivative of both sides. Once I do this, I'm going to end up with u prime equals, and the derivative of the sine is the cosine of y times, because we're taking the derivative with respect to x, y prime. And this means if I solve this for y prime, then I'm going to get u prime over the cosine of y. And if we look at my triangle, the cosine of y is the adjacent over the hypotenuse. So u prime gets to stay in the top, but the cosine of y is going to be the square root of 1 minus u squared. And that's going to give me my inverse sine derivative formula. So if I have the inverse sine of u, I'm going to have u prime on the top and the square root of 1 minus u squared in the denominator. Well, let's do the same thing for cosine. We're going to take the u and construct the triangle for y. So this means the cosine of y is equal to u. So that means your adjacent side and your hypotenuse side are defined for you. And you can use Pythagorean theorem to figure out your opposite side. Then I can do the same thing. I can take the derivative of both sides and then solve for y prime. And then replace the sine of y with the information I have from the triangle. And the sine of y is opposite over hypotenuse, and the hypotenuse is 1, so I just end up with that. So the derivative of the inverse function is negative u prime divided by 1 minus u squared, the square root of. And the last one I'm going to work through with you is the tangent, the inverse tangent of u. So for this one, same thing. I let u equals the tangent of y. I build up the reference triangle for the angle of y. Now tangent is the opposite over the adjacent. And so using Pythagorean theorem, I built that up for the hypotenuse. And then if I take the derivative, remember that the derivative of the tangent is the secant squared. And then don't forget that y prime. And then I'm going to solve for y prime. So y prime equals u prime divided by the secant squared of y. And then I replace the secant squared of y using this reference triangle. So remember that the secant squared of y is the reciprocal, I'm writing it backwards, the reciprocal of the cosine squared of y. So the cosine is adjacent over hypotenuse. So adjacent over hypotenuse, but it's squared. And when I take and I divide by a fraction, I multiply by the reciprocal. So I'm going to multiply by the reciprocal of this bad boy. Also, when I square square root, the insides come out. So this is for secant squared y, I'm going to end up with 1 plus u squared, no square root. Cool, eh? And that's what goes here. So the derivative of the inverse tangent is u prime over 1 plus u squared. The rest of the formulas you can derive on your own if you feel like it, but they are a little hinky, so I won't walk you through it. I figure I've tortured you enough with the proofs. But you do need to memorize them. And although your book gives these derivative formulas as x's instead of u's, let's just go ahead and focus on the u's because it's a lot easier. All right, let's look at these functions and let's take the derivatives. Find the derivative of the function, simplify where possible, blah, blah, blah. All right, let's look at a couple examples of these. I am going to take the derivative of the inverse sine of 2x minus 1. So the first thing I'm going to do is I'm going to say, okay, let's let's use the u substitution here. Let's figure out what u is, and let's figure out what u prime is. So per usual, we say that the u is the inside, so we're going to use it as 2x minus 1. And that u prime is going to be 2. And then let's just remember the formula. The formula for the derivative of the inverse sine of u is equal to u prime divided by 1 minus u squared, the square root of. So let's plug that stuff in. So the u prime, that's going to be 2. And the 1 minus u squared is going to be 1 minus 2x minus 1 squared. But we're not done, because notice it says simplify where possible, and this thing is definitely possible. So I'm going to drag it up here. So f prime of x, my top I'm going to leave like that. Now my 2x minus 1 squared, give myself some room. So 4x squared minus 4x plus 1. And all of that is being subtracted, okay? All right, don't forget, if that ever messes with you, you can just FOIL it out. But whenever I square something, I really just think about it like this. I take the first term, square it, and then I add to that the first times the second times 2, which in this case, the second one is a -1. That's why it's minus right there. And then plus the second one squared. All right, I digress. So let's distribute the negative sign. Watch yourself in those negative signs. And then notice the 1's cancel. Super cool. And when the 1's cancel, I can do some factoring. In fact, in the square root, I can factor out 4x. And then what I've got left, as I factor 4x out, is 1 minus x. Well, I can't take the square root of 1 minus x or the x, but I can totally take the square root of 4. And so that makes it so that the 2's on the top cancel. Neato. Find the derivative of the function, simplify where possible. So this one is going to use the quotient rule. So let's do that. Okay. So remember a couple things. The derivative of the inverse cosine of u is equal to negative u prime over the square root of 1 minus u squared. And then the quotient rule, of course, is that low d high minus the high d low all over the low squared. All right, so that's that quotient rule. Let's combine those two. So f prime of t. F prime of t is going to be low d high. So the low times the derivative of the inverse cosine. Now in this case, the inverse cosine, keep in mind that u is t, and even though I'm sorry, I wrote this as the derivative with respect to x, but we are taking the derivative with respect to t. U prime is just going to be 1. So when I take the derivative of the inverse cosine of t, it's just going to be -1 over 1 minus t squared, the square root of. So not too bad. Then I'm going to subtract from that my high d low. So the inverse cosine of t times the derivative of the low, which is just 1. And then that's all over t squared. Not too bad, right? All right, let's clean it up. So this t multiplies by this -1. And this just simplifies to that. And then I've got t squared. Well, I want to do a couple of things here. First of all, I'm going to create an LCD situation here of 1 minus t squared. I either can multiply through by the LCD or build up the LCD. It's up to you. It's all good. If I multiply through by the LCD, this one has the LCD, so I'm going to get -10 here. This term is going to turn into this chunk of algebra here, negative inverse cosine of t times the square root of 1 minus t squared. And that's going to be all over 1 minus t squared, the square root of, all over t squared. Which, I don't know if you know a little fact, but the denominator of the numerator is the denominator. I know, I'm sorry I said it like that, but it's true. In other words, if I have a divided by b divided by c, it's like saying a over b times 1 over c, or a over bc. So that's what happened here. And that's my derivative. I can't simplify that any more than that. All right, you guys, that is it for this section of inverse trig greatness. Good luck to you on your homework. And be diligent. Keep your wits about you. Don't get lost in the woods of all these derivative functions. And do yourself a favor. Every time you use a derivative function, write it down. Because that way, that'll help you memorize it for the test. All right. See you next video.